Welcome to July 19th LeetCode Challenge. Lowest common ancestor of a binary search tree. Given the binary search tree, find the lowest common ancestor of two given nodes in the binary search tree. According to Wikipedia, the lowest common ancestor is defined by between two nodes P and Q as the lowest node in T that has both P and Q descendants. Also know that we allow the node itself to be a descendant of itself. So given this binary search tree here called root, where 6 is the root of the root node, what we have is we want to find P equals to 2 and Q is equal to 8. So we have it right here and right here. And we want to find the root node that connects both of them together. So the lowest common ancestor, which is connected to 6. And therefore we return 6 as the output. Given the same tree here, we have P equals to 2 this time and Q equals to 4. So 4 is connected to 2, and 2 is a root descendant of itself, So therefore, the lowest common ancestor is 2, because 4 is connected to 2, and 2 is a descendant of itself, so therefore everything is connected to 2. Similarly, we have a root tree, binary search tree here, where we have 1 connected to 2, and 2 being the root node, therefore we return 2 because 1 is connected to 2, and 2 is a descendant of itself. So therefore 2 is the lowest common ancestor. Let's see, we're given some constraints here. So one important to note is that all the node values are unique. Therefore we're able to search through the binary search tree and so that without being by comparing the values. So let's the lowest common ancestor of P and Q will be the lowest common ancestor of both of them. So what we want to do is develop an algorithm where we traverse the tree from the root node, so starting here, and we're going to go left, right, left, right. So therefore, we can also do right now. We're going to does this recursively, but I'm going to try to do it iteratively. So if both nodes P and Q on say the right side of the tree, then we continue the search on the right side of the tree, starting with step 1 again. So we treat if we go here, we treat this as a node, that root node instead. So if both nodes P and Q are on the left side, however, we treat 2 as a root node, then we continue going down iteratively. So we will find the lowest common ancestor of P and Q from the subtrees. Hence, we're going to return lowest common ancestor, and we find the root node that contains both of them. So let's write out some ideas here. So this is a ranked easy one. There's actually a question called lowest common ancestor of a binary tree, which is a medium-sized question, which actually works. The solution works for this as well, but this is a bit easier. So while the root node is not empty, or root node exists, what we're going to do is we're going to traverse our P, our left side and our right side. So let's go if root dot value is less than root P dot value and root dot value is less than Q dot value, then what we want to do is return assign root to be root dot right. So the reason why we could do that is because it's a binary search tree. That means everything is already everything is sorted according to their values, right? So if the root is less than the P value and the root is less than the Q value, then we want to reassign root to be equal to right. Assign else what we want to do, else if I should say, else if root value is greater than P dot value and root value is greater than Q dot val, then what we want to do is return root assign root to be root dot left. Else, if all these doesn't work, just return the root because we cannot. The root itself is the actual original root on top, which means everything is connected to there. So yeah, P does not equal to Q, and then Q and P obviously has to exist for this to work. Alright, let's run the code, and 6, let's see. Alright, accepted. So time complexity wise, it would be big O of n being worst case scenario because n is the number of nodes in the root tree. Because in case we do have to traverse through the entire tree itself to find the roots of left and right, then that's the worst case scenario. So big O of n for time complexity. Space complexity is we're returning the it's big O of n because the maximum amount of space utilized by the actually it would be, yeah, it's a recursion stack. So even though we don't do this recursive, no, actually it'd be big O of big O constant time, because we are going through each node individually and then we just return the root. So yeah, it'd be big O of a constant space. Alright, awesome, that's it. Have a great day, guys.